Welcome and thank you for your interest on this talk, and thank the organizers for letting me talk about my project, which is on Minkowski Functionals as a tool to study non-Gaussianities and anisotropy. In particular, how we extend this formalism to CMB polarization. My name is Javier Carrón Duque. I'm a postdoc in INFN in Tor Vergata, and this is some work that I've been doing in collaboration with the people in the Cosmology group there. The talk today is structured in this way. First, I will give an introduction on Minkowski functionals. Then I will talk about how we extend the formalism to polarization. Then I will talk about other applications that we are interested on of Minkowski functionals. And I will finish talking about the software that we have developed and we made publicly available for the community. And of course, I will conclude at the end with the main points. So let's start with Gaussian fields. We know that Gaussian fields are easy to describe. If we have a physical process that produces an observable Gaussian field, the process is described by the two-point correlation function. So essentially everything there is to know, we can obtain it with the two-point correlation function of the angular power spectra in the case of the CMB. What happens if we apply this tool, the two-point correlation function, to a field that is not Gaussian? Well, nothing really, no? The two-point correlation function is blind to non-Gaussianity and anisotropies. So in order to understand if there is non-Gaussianity in the field, and if there is, in order to extract this information, the cosmological community have adopted a series of tools. Tools like the 3 or 4-point correlation functions, the bispectra, trispectra, or tools like the extrema statistics, the number of maxima, number of minima, number of clusters, number of voids, these kind of things. Also things like the Betty numbers and many others. But in particular, in this talk, I will focus on Minkowski functionals. And before I continue, I just want to say that when we talk about non-Gaussianities, we often focus on FNL. And FNL is very important. It's a parameter that characterizes a certain kind of non-Gaussianity. And if we measure it, great. But it's not all the possible non-Gaussianities. So we still need additional tools that allow us to explore the full space of possible non-Gaussianities beyond FNL. And one way to do that is with Minkowski functionals. Minkowski functionals are high-order statistics. This means that the information contained in the Minkowski functional is independent from the information in the 2, 3, 4-point correlation functions. So there is always something else in this kind of statistics. So let me define them. Well, let's start with your favorite field, temperature, the density field, whatever you want. And let's imagine that this top right plot here is your field. Now we select a threshold, U, which, for example, is 2 sigma, the 2 sigma of the map. Now we select all the points on the map that are above 2 sigma. So in this example, it will be the white regions on the bottom right plot. Now these white regions constitute the so-called excursion set at 2 sigma of this field. And now this set can be characterized by 3 quantities. First is the total area of the set. Then we have the length of the boundary of this set. And finally, we have the number of disconnected regions minus the number of holes that they may have. This is called the Euler Poincare characteristic and it's a topological quantity. These 3 quantities together are called the Minkowski functionals. And they can be proven to characterize the excursion set under certain desirable conditions. So, okay, you may be saying, yeah, I have my field, I can compute these quantities for different thresholds, but what information is this giving me about non-Gaussianity? This in principle is not related at all. And yes, but the good thing is that for Gaussian isotropic fields, these quantities are very accurately predicted. So for isotropic Gaussian fields, the expectation value of these quantities is known, but also the variance is small. So we have very accurate predictions of what these numbers should be for all thresholds. Now, I'm not going to enter into the mathematics of why this is the case, But I just want to show that the formulas are actually very simple. So the expectation value is just a multiplication of three independent factors. The first one depends on the threshold, depends on u. It's not the same if we compute these quantities as at 2 sigma, at 3 sigma, at 0. The values are different, but we know the exact behavior with threshold. We know these functions. The second factor depends on the space where we are working on. So if we are working on the CMB, this will be just the surface of the sphere, so 4 pi. If we are working on the CMB with a mask, it's just 4 pi f sky, right? The fraction of the sky. So it's just a multiplicative factor. It affects all the thresholds the same, it's completely independent for everything else, and it's just a factor. There is no mixing, there's no coupling, there's no leaking, there's nothing strange. This is different from the two-point correlation function, right? Where there are a lot of effects that can take into that we have to take into account. But for Minkowski functionals, it's very easy. It's just a multiplicative factor. And the last thing that comes into the expectation value is this mu, which is just a single number that we can think about like the correlation length of the map. So this is just a quantity we can measure on the map, or we can measure with the power spectrum. But this is just a single number, and we just multiply the expected value by this quantity. So just to actually show that there are easy formulas with easy profiles, these are the functions as a function of the threshold for an isotropic Gaussian field on the sphere. So it's fairly simple predictions. Now, if we measure the Minkowski functionals on your favorite map and it doesn't follow these predictions, then your map is not Gaussian or isotropic. This means, thanks to this, people have applied Minkowski functionals to different observables. The first example is CMB temperature. We know it's very close to Gaussian, but we have to test it with different tools. And people have used Minkowski functionals to test this in a blind approach. So we don't need to assume any theoretical model. We just compute the Minkowski functionals and see that indeed they look like these predictions. These have been done in the Planck papers, the isotropy and statistic paper, and indeed they don't observe any deviation as expected. But these tools have also been used in other observables. For example, in the weak lensing maps. These maps are non-Gaussian because they are produced by the distribution of matter in the universe. And there have been a very rich recent literature. But for example, in one of the latest paper from Euclid, Preparation 29, they compare the expected errors, the Fisher forecast, for a couple of different cosmological parameters using just the angular power spectra in blue or just Minkowski functional in yellow. And we can see the information is actually different. And of course, they are not exclusive. We can use both of them and we can combine them to obtain a green profile. Minkowski functionals have also been used to characterize foreground emission, galactic emission in synchrotron and galactic dust. And because they are very not Gaussian, of course. And they have also been used to analyze the large scale structure. For example, the paper by Spina is on 21 centimeter simulations. But also a very recent paper from Liu et al. Have shown a similar plot as before. This is the forecast errors for different cosmological parameters, just using the power spectra in blue or the Minkowski functionals in yellow. So we see that the information is actually very different and complementary. Now let me talk about how we use Minkowski functionals and how we extend this formalism to polarization. Now, when I introduced Minkowski functionals, I was talking about the excursion set, right? Like where your field is larger than 2 sigma. This only makes sense if your field is a real field. But polarization is a complex field, it's a spin-2 field with this rich structure. So we cannot directly apply Minkowski functionals. There are different ways to do this, and the first way we studied is just with the modulus of the polarization, p squared. So this is q squared plus u squared. Now, this is a real field, so we can use Minkowski functionals as usual, but this is not a Gaussian field. This is more like a chi-square field with some spin effects. So we managed to take this into account and obtain the theoretical expectation for this kind of fields, which we can see in this slide. Now we have also verified with simulations that the theory and the simulations are perfectly compatible. And we can see the top panel is the value of the Minkowski functionals with the error overplotted. It cannot be seen because it's that small, but the prediction is really accurate. But yeah, we can see that there is perfect compatibility. In the middle panels, we have the residuals with the standard deviation on the simulations. And in the third planet, we have the comparison of the mean of the simulations with respect to theory. So still, it's really good agreement. Now we have also analyzed Planck data. Now, Planck polarization data is not isotropic because of the observational strategy. It has anisotropic noise, which affects the level of anisotropy of the map. So we cannot compare it with the isotropic formula, the isotropic expectation, but we can compare it with realistic simulations that take into account this observational strategy. And we did this and observed that the Planck maps are actually very compatible with the realistic simulations. So there is no unexpected non-Gaussianity. Now, I've been talking about p-square, but I said before that the polarization field is very rich, it's complex. So if we analyze only p, we are losing information. The same if we analyze only e or b or q or u, we are losing information if we analyze a scalar field. Mathematically, it is possible that E and B are Gaussian fields, but still the complex spin field is not Gaussian. This can happen. So it's not enough to analyze the scalar projections. We have to analyze the whole polarization field as a single unit. And the way we do that is with a new formalism in the mathematical literature, which consists in considering the spin field, the polarization field, not as a complex field on the sphere, but as a real field on a higher dimensional manifold. This is SO3. If you're interested, this is a three-dimensional space. Now, the theoretical predictions here were significantly more difficult, but we managed to produce them, and we have verified with simulations that like everything seems to be compatible. So the theoretical formula seems to be very compatible with the Gaussian simulations. So, well, and we want to apply this formalism to future data like lightware. So stay tuned for that. For now, Planck data doesn't seem to present any significant deviation, but of course we want to keep studying it. Now, I want to talk about a couple of applications very quickly. The first of the applications that we are studying is galactic dust. So it is not trivial at all to produce realistic realization of the polarized dust. Right? Dust is very non-Gaussian. It comes from our own galaxy. The distribution is very complicated. And because of that, there are several models, like entire groups dedicated to try to get realistic simulations. This is very important then for things like component separation and these kind of things. What we are trying to do is just to take models that exist in the literature, like the models from the PySM, the Planck Sky model, or generative adversarial neural networks that have also been proposed, and just try to analyze the level of non-Gaussianity, the level of anisotropy that they present, just by using Minkowski functionals. And stay tuned for the results. We are analyzing them. I'm also working, my other project is on cosmic filaments. So if you're interested on cosmic filaments, check it out. We have a nice catalog. But this is just to say that I'm interested in the large scale structure as well. So of course, I'm interested in how the Minkowski functionals can be applied to the large scale structure, the 3D density field. Now, this field is not Gaussian, there is a lot of information in the non-Gaussianities. Now, this information could be primordial as a consequence of inflation, but it's mostly late universe non-Gaussianities as a consequence of gravity and also baryonic effects. Now, there are several questions that arise, like, can we use Minkowski functionals to distinguish between them? Can we include the effect of gravity in the theoretical predictions? Now, can we use Minkowski functionals to constrain cosmological parameters? Well, some recent literature has shown that yes, at least with forward modeling, with simulations. Other than that, we don't know if there is a more efficient way. Now, how do Minkowski functionals compare to other statistics, like the bispectrum or the maxima distribution? Well, we don't know. There could be better for some theoretical models or present different degeneracies between parameter, different robustness to systematics. This is something that is now starting to be studied, and it's really exciting. There is still a lot of work to do. Now, Minkowski functionals can have many other applications. We just saw some of them. If you have some idea in mind, please talk to me. I will be very happy to discuss any new idea. So the last point of my talk is about Minkowski. This is a software that we have developed. It's a Python package to compute Minkowski functionals. This package is fully documented and it's also modular. We have a module for the theory, so the theoretical predictions of different kind of fields. We have a module for the data, where we can compute actually Minkowski functionals on 2D, 3D MP arrays, but also for Hilpix maps, these kind of things. So it's quite flexible. And we also have a statistics module. Of course, we're focusing on Minkowski functionals, but we also have things like maxima distribution, minima distribution, and we want to expand all of these modules in the future. And of course, they are compatible with each other. Now, all of the modules hopefully are easy to use and easy to expand. So if you're interested in this at all, feel free to have a look and let me know if you have any problem. Here, you can stop, pause the slide if you want, but this is just to show that the code is actually very easy to use. And it's fully documented in any case. So this is just my takeaway points. The first is that Minkowski functionals are useful tools to study non-Gaussianities. We have expanded the formalism of Minkowski functionals to CMB polarization with p², but also with the full information complex map. And we have created this software, Minkowski, that hopefully will ease the application of Minkowski functionals to the cosmological community. So thank you very much for your attention, and please let me know if you have any question or anything you want to discuss.